Good morning and welcome to today's webinar, Reducing Arc Flash Risks in Your Workplace, sponsored by I-Gard Corporation. I'm Mike Eby, Group Editorial Director for EC&M. Before we get started, I need to cover a few housekeeping items. If you have any technical difficulties during today's session, please put your question in the questions window and our technical experts will help you. We recommend that you disable any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation. But feel free to send your questions in at any time. You can simply type your question into the Ask a Question window on the side of your screen and hit the Submit button. To download a copy of today's presentation slides, look at the Event Resources tab located below the Ask a Question box. You'll also see some other assets that are available for download. And we'll also be recording the session today, and we'll make that recording available on the EC&M website within the next week. And you'll be notified by email when the archive is available. Now I'd like to introduce today's speaker. Sergio Panetta is VP of Engineering at I-Gard Corp. He's a graduate of McMaster University and has more than 3 decades of electrical engineering experience in switchgear design, commissioning and troubleshooting, and power system protection and power system grounding. He continues to actively increase awareness of electrical safety on a global front. Sergio is a senior member of the IEEE, member of IET, and has been awarded consulting engineering status with the PEO professional body. He's a member of several industry working groups and committees and is the author and owner of several U.S. patents related to electrical safety. Sergio, welcome today, and I'm going to turn it over to you now to deliver your presentation.
Thank you, Mike, and thank you to EC&M for making this very easy for us to actually do. I mean, it's ironic that we're discussing reducing arc flash risk in your workplace, because last week I was at the electrical safety workshop in Tucson, and if you're a safety professional, I would highly recommend going to that particular conference from IEEE. So again, we're going to discuss arc flashes. So the National Fire Protection Agency, Association, defines an arc flash as a hazard, as dangerous condition associated with release of energy caused by an electric arc. An arc flash occurs because of breakdown in insulation between 2 conductive parts. It can be caused by human error, equipment failure, environmental factors, and ground faults, face-to-ground ground faults and face-to-face ground faults. So when you have electrical insulation, you have conductors. If there's a breakdown in insulation, really what happens is you get 2 conductive parts with a potential difference cause an arc flash, and how severe a fault that is depends on how much energy is released. So about an arc flash, obviously we've all heard how hot it is. It's very hot at the center of an arc flash. Loud noise, copper ends, actually vaporizes. So I'm not sure of the volume, but it actually does vaporize because it's a little tiny explosion inside the copper. You can think of it that way. I'm not a physicist, so I'm not going to try to explain how an arc consists of. And you have molten metal and shrapnel spraying at 700 miles per hour. So this is why we have to wear protective equipment, to protect against the heat, against the sound, against the shrapnel. So arc resistant proof clothing will develop to protect the worker from such physical harm. Temperature, burns, hearing, obviously you have the shrapnel coming at you, so you have to worry about how to protect yourself. How does the electrical worker protect themselves with that? And the industry has done a tremendous job developing arc-proof wears, so that the electrical worker can be protected in the event that this happens. It doesn't happen all the time, but it does occur. And when it does occur, you should be protected against it. And of course, when an arc flash occurs, I'm going to use the word arc flash quite a bit here, but when an arc flash occurs, there's not only a threat to the personnel, but and as an owner, you really want to keep that equipment running or try to minimize the downtime and get it back into operation. So on a yearly basis, according to National Safety Council, 30,000 arc flashes occur every year. 7,000 burn injuries, 2,000 hospitalizations, 400 fatalities per year. The average cost of a medical treatment, especially in a burn unit, $1.5 million. The employees can be out for 8 to 12 months. And it's a horrendous cost on the insurance company, the electrical industry, the manufacturers. And it can be like $10 to $15 million on average per year. So what causes an arc flash? Human error. Obviously, we all make mistakes. Many of us have screwdrivers with a little bit of the steel burnt off. I know I have some, and I shouldn't. I'm not qualified to work on electrical equipment. This is just working at home, thank God. Because if I was working on electrical equipment, I don't know if I would have lived this long. Because I'm, how can I say this? Always meticulous in what I do. People are working on or near electrical equipment, so this is an arc flash. You don't actually have to be working on it. You can be near the equipment and be subjected to an arc flash. Failure to follow proper work instructions, inadvertent contact with live conductors while working. Obviously, this is why we have little nicks on all of our screwdrivers. And a ground fault. A ground fault has a potential of escalating into a phase-to-phase or a three-phase arc fault. And the ground fault can occur anywhere. So it's not always where you have the optimal protection to protect against that. ESFI has indicated that 2,110 electrical burn injuries in manufacturing establishments and typical causes of arc flash incidences. So you can get statistics like these. The construction industry has a lot of burns, and you can see why, because they're working quickly to try to get everything done on time. Manufacturing, utilities, financial activities, all these industries have been typecast, and you know how many injuries occur in every single industry. So electrical safe work condition. There's a lot of agencies that are trying to protect the workers. Arc flash in a workplace. So basically we've got OSHA and NFPA 70E in the United States. 1584, IEEE 1584 is a guide to performing arc flash hazard calculations. So you know what you need to wear to be completely safe. The clothing, it's an art form basically, because there's a lot of probabilities that someone has to look at to design the proper clothing and to approve the proper clothing. ASTM, the standard for testing clothing, has a probability of 50% of preventing second-degree burns if you wear the appropriate PPE. So how well do you want to protect your employees? Are you saying 50% is good or 50% is not a good chance of? You want to protect 100% of the arc flashes or 50% of the arc flashes from causing second-degree burns? So these are things that we have to try to balance in the workplace, or making the decision of what to wear to protect the worker. And in Canada, we have Z462. Of course, this is a new code cycle. So the year 2024, we have new cycle and Z462. So in both cases, we try to use get into a de-energized condition. Article 120 on NFPA 70E and the corresponding article in Z462 requires electrical equipment and machinery greater than 50 volts to be placed into an electrical safe work condition. And they describe how to do it. So you have to de-energize the power conductors, any stored energy, and put measures in place to ensure that anyone working on that equipment is going to be safe from accidental contact with exposed conductors. This means completely de-energizing the equipment, conductors, or circuits before employees could begin to work. One thing that's important to have to look at secondary sources. So some panels have not only the mains of 480s coming in, but you also have maybe 120 volt AC or DC control power coming in. So you have to be aware of the particular equipment that you're working on. And this is why only qualified people are allowed to work on equipment. I've designed a lot of equipment in my life. I'm not qualified to work on any of it. So the employer determines who is qualified to work on their electrical equipment. Even though I may design something, if I go into someone else's facility, I'm not qualified to work on it. So to assist with this, we've developed an absence of voltage tester. An absence of voltage tester is used to verify the absence of voltage. This is the tricky part, okay? We can visually see that the voltage switch may be, the power switch is open. We may be able to see it or may not be able to see it, but we can't do it from a safe position because we have a panel in the way. So we have to verify the absence of voltage. And I think in North America, the only region that asks workers to verify the absence of voltage. So we have to de-energize from hazardous voltage before maintenance occurs, reducing the risk of electrical incidents such as arc flash and shock. So again, the industry has done such a great job preventing arc flash, but we've not done a great job in preventing shock hazard. And more people are hurt or killed by shock than by arc flash. So this particular device gives you 3 red LEDs and says it's undoor. This is a permanently mounted device connected to every disconnect switch or the disconnect switches that you want to consider. And it says it has 3 indicating red lights to indicate that it's unsafe. When you shut off the switch, you press the test button. When you press the test button, it's going to go and measure the voltage face to face to ground. It's going to look at AC voltage and DC voltage, and more importantly, it's going to check to make sure that it's functionally working properly, has an internal protection circuit diagram, and it's going to make sure that it's connected to the phases of your system and verify that it's connected to the phases of your system. And only if you get less than 3 volts face to face and face to ground and everything is connected properly and everything is working properly, you're going to get 3 green lights indicating that the point at which you have the conductors connected is de-energized. So owners and consultants have the duty to arc flash in electrical safety, designing for electrical safety. So we have to reduce the likelihood of exposure. And this year in the code revision 2024, high impedance protective test points have been introduced. And I think it's been introduced more to prevent shock than arc flash. So it allows the worker to measure the voltage, troubleshoot the circuit from outside the cell, inside the cell, or opening the door and measure voltage. So The voltage presence is indicated through redundant LEDs. So you have visual indication that the voltage is live. There's 2 LEDs per phase, and they'll flash alternately. AC cycle, one on the negative C cycle. You have L1, L2, L3. So you have one conductor going to every single phase and one conductor going to ground. It's touch safe points, so you can measure the voltage. You can't put your fingers in there. You can only put the probes of the voltmeter in there. So we try to minimize shock when you do that. No power supply, so it's not really a unit that requires power other than the voltage on the bus. And it's up to 1,000 volts AC, category 4, and the test points are 0 to 1,000 volts. So you can measure the voltage on the bus, but the indicating lights go up to 1,000 volts. And we have the IAVT plus. This is both units combined. So you have the VTI on the top and the IAVT on the bottom over here. So this is in order to help people understand better what's happening with their system. So the absence of voltage tester is used specifically to test for the absence of voltage. But the test portal is used to measure voltage and troubleshooting, all from outside of your cell. No longer do you need to go inside the cell and do some troubleshooting. The voltage indicator is tested to UL 61010. Measure voltage and perform tests. Again, you don't have to open the door to do any voltage. We also voltage source, so you can actually test your meter to see if it's working. And these 2 points come from a source inside the AVT, and the AVT is listed to UL 1436 EC 61508 to require SIL3 safety intrinsic level, and it's a strenuous test to perform. The AVT is powered by the voltage on the bus, but it has an internally charged capacitor, a supercapacitor, which is your power source for the indicating lights, because you need power when the system is de-energized. So we try to use a supercapacitor rather than a other source such as NFPA 70E allows the energized work if an employer can demonstrate that the de-energized introduces additional hazards. So you can work live, but the employer has to demonstrate that energizing causes more of a hazard than working on it live. So you have to calculate the risk of having an arc flash. This is why this topic of this subject is the risk, minimizing the risk, not the arc flash hazard itself. The arc flash hazard is the arc flash hazard, but we're trying to minimize the risk of having an arc flash hazard. So you have to make sure that the people are trained and certified. We have 50 volts of energized work. If you have more than 50 volts, and 70E requires documentation including energized work permits for energized work, and Article 130.2b details permit requirements. So the onus is on the employer here to ensure that they authorize the employee to perform work energized. So the onus is changed from the employee. You have to protect the employee, but the employer, who assumes the responsibility if that person gets hurt, to authorize the work. But everything else needs to be done as well, so no one else gets hurt. And gets hurt, period. That's what we want to do. So what is the probability of an arc flash occurrence? And what if it does occur, what would be the magnitude of its severity? So NFPA 70 again throwing you to reduce the likelihood of exposure. If you look at Annex O 2.2, the owner and designers have to reduce the likelihood of exposure and reduce the magnitude of exposure. So reducing the likelihood of exposure. There's very few things you can do to reduce the likelihood of exposure. One of them is not work on it at all, but you have to assume everything is energized until you prove it to be de-energized. So working on it, energized is energized work. So ground faults and system grounding. According to the Industrial Power System Grounding Design book, written by Duncan Jacobs, Mr. Shields, and Conrad St. Pierre, 95% of faults begin as ground faults. 4% are phase-to-phase faults. 1% are three-phase faults. The 1% three-phase faults that occur are not necessarily three-phase faults, but they're always more or less caused by human intervention. Think of a forklift driving through a bus duct. That's a three-phase fault, but it's caused by not the deterioration of the system, but by human intervention. You're taking the panel off of a piece of switchgear. It falls onto the three-phase buses. You're causing a three-phase fault. So this is what happens. There's very few times that a three-phase fault is going to occur. And IEEE 1584 states that you have to take all faults are considered three-phase faults to calculate the incident energy. Well, it occurs less than 1% of the time. So a ground fault is an unwanted connection between the system conductors and ground. Ground faults often go unnoticed and cause havoc. If you set your protection too high on a breaker or a ground fault element of your protection system, you may not be able to detect the ground fault. If you have a high resistance fault in a solidly grounded system, you may or may not detect the fault. 9 times out of 10, ground faults can lead to hazards, safety hazards such as fire and electric shock. So we have to be a little careful here because this touch and step potentials on solidly grounded systems can be quite high. Ground faults may occur due to various factors such as loose connections, worn insulation, moisture, or external natural causes. And I've seen some external natural causes like ducks flying into sitting on top of a transformer, and they have a huge wing, the ground fault because they touch base and ground. So you can get a ground fault from almost anything. But to discuss ground faults, we need to look at system grounding. So how do we ground an electrical system? So an ungrounded system in industry is a system that has no internal connection between the phase conductors and ground. Most of you are not familiar with this, but prior to 1950, this was a very common method of grounding, ungrounded. So if you have a choice to do something, do it. So there's no connection between any of the phase conductors and ground. This is known as an ungrounded system. Now, when you have a ground fault, the current goes from the faulted phase. So one of the phases is going to contact ground. When it contacts ground, it needs to go somewhere. So ground fault current always has to return back to its source. Because the system is ungrounded, there is no return path. The only path you have for the current to go in an ungrounded system is to the other phases through the capacitive coupling, and we'll discuss that a little bit. It's very difficult to locate a ground fault in an ungrounded system because there's nothing to detect. You have no current, and the only thing you're going to see if you measure phase to ground on is if you have a 480 volt system, you're going to measure when the system is healthy, 277 volts to ground on each phase. If you have a ground fault, you're measuring 240 volts to phase on the two ungrounded phases and 0 volts to ground on the, and unfortunately, the voltage applies to that phase conductor throughout your entire facility, so you can't find the ground fault. So we're susceptible to transient overvoltages in an ungrounded system because there's no, think of it as charging the capacitors of your system. You have an arcing fault, you're constantly charging and discharging the resistors, and depending where that fault, the time of that fault, you could be arcing at the positive cycle of the AC wave or the negative cycle of the AC wave. So you're constantly changing the voltage on those capacitors, and you can have the 6 to 8 times normal system voltage with respect to ground. If a second fault occurs, then you have a phase to ground to phase fault, and something will trip. So you can't find the ground fault, and the code says that you indicating lights. So lights are connected from phase to ground. So when you get a ground fault, one of those phase indicating lights extinguishes, and the other two get brighter. So that's how you can tell if you have a ground fault. So the difference between, think of it, if the difference a burnt out light bulb and a ground fault is minimal because the other two are always going to look brighter. So if you look at this particular schematic between A phase, B phase, and C phase on the voltage on the left-hand side, you have capacitive coupling from the phase conductors to ground. So think of the cable as a distributed capacitor because you have two potentials isolated from each other from an insulating medium. Well, that's the insulation on your cable. So that's a capacitor. And this capacitor is distributed throughout your entire facility. So those capacitors are charged and discharged when you have a ground fault. So the first, when there's no fault on the system, the neutral point, the apparent neutral point, is at ground potential. But you still get 277 volts phase to ground on neutral because it's a grounded system. When you get a partial fault, you start to elevate the voltages, and when you get A phase that's actually contacting ground, you have 480 volts on C and B phase and 0 phase to ground. Now, it's important to determine, to see in this particular diagram, we do not energize ground in an ungrounded system. You can still touch the enclosure. All we've done is shifted the vector relationship with respect to ground such that B phase and C phase are now 480 volts to ground instead of 277 volts to ground. So we just shifted the neutral, the apparent neutral, up 277 degrees due to the ground fault. And the current you can see here, the capacitive coupling, that's when we have another hour, we can explain how that happens. So what do the standards say about ungrounded systems? The Red Book says that accumulated operating experience indicates that in general purpose industrial power distribution system, the overvoltage instances of operation reduce the useful life of installation. Yes and no. I would think this is a problem more above 5 kV than below 5 kV. For this reason, the NEC says that if you have an ungrounded or a resistive grounded system, you have to use higher insulation cable depending on the length of time your ground fault is on the system. So if your ground fault is on the system between 1 minute and 1 hour, you have to use 133% rated cable. If your ground fault is on the system for beyond 1 hour, you have to use 173% rated cable, but that only occurs above 5,000 volts, not 5 kV, but 5,000 volts. So it's not necessarily a problem in low voltage, it's more a problem in medium voltage. So in ungrounded systems from the Green Book, destructive transient overvoltages. You have to keep in mind, you can get up to 6 to 8 times transient overvoltages with respect to arcing ground in an ungrounded system. Arcing ground faults are likely going to occur in a motor someplace. And the Buff book, is that the Buff book? It says the same thing. Solidly grounded systems. So you can see here that the solidly grounded system, you have 3-phase conductors. The midpoint of all those coils connected to ground with no intentional impedance between them. So you have and when you have this type of system and you have a ground fault, remember, a phase touches ground, you use the bonding network of your entire facility to get back to that ground point that's going to connect it to the neutral, and you complete the circuit. So a ground fault just basically completes the circuit. But what happens is because you have no intentional impedance, you have a tremendous amount of current that's flowing. And the codes, both the NEC and the CEC, say that if you have a solidly grounded system and your voltage is higher than 150 volts to ground, greater than 1,000 amps, you must have ground fault protection. You have severe equipment damage where the fault occurs. Sustained arcing can release mechanical energy, causing severe damage and injury, likely escalating a single-phase fault to a 3-phase fault. So let me explain this a bit. Remember, Ducky Jacobs said that 95% of all faults begin as single-phase to ground faults. So in a solidly grounded system, because faults begin as single-phase to ground faults, you have a high probability of a single-phase to ground fault escalating to a phase-to-phase and 3-phase fault and an arc flash event. Whereas in the ungrounded system, you didn't have that problem, you had other problems. So again, the Red Book and the Buff Book all say that solidly grounded systems have high magnitude destructive current. And danger sustaining arc flash of ungrounded fault probability due to systems. So high resistance ground, same as the solidly grounded, except we put a resistor between the neutral point and ground if you look at the schematic on the left, on the right, sorry. What happens now is, let's assume we have a volt system. We put a 55 ohm resistor in there. 55 ohm resistor is going to be about the size of a bread box. Now I'm dating myself, right? So a bread box, and that protects your entire facility. You still elevate the neutral, even though the neutral is not distributed. You can't distribute the neutral in a high resistance grounded system, but the neutral gets elevated to 277 volts. Well, 277 volts divided by 55 ohms gives you 5 amps. So you limit the fault current, the same fault that we had in scenario where we have thousands of amps flowing. We put a 55 ohm resistor in here, and now we have 5 amps flowing. Same size transformer. Doesn't matter if it's 1 kVA, 1 MVA, or 5 MVA. 55 ohm resistor there will limit your fault current to 5 amps. And the NEC and CEC say that if you limit your fault current to a low value, CEC says 10 amps or less, NEC says a low value. If you look at 250.36 in the NEC or 10-300 in the CEC, and those are the Canadian, the National Electrical Code. All systems 5 kV or less provide service continuity. So this is for facilities that can't tolerate outages for a ground fault. So on one hand, we have a solidly grounded system, which you have a ground fault, you have to trip by code. On the other hand, we have a high resistance ground in the system. The same ground fault allows you to keep running. And we provide you with the tools to look for the ground fault. So what does NFPA 70E say? High resistance grounding is an arc flash mitigation technique. It reduces the likelihood of exposure. If you look at all the other incident energy reduction methods, they only limit, not only, but they limit the severity of exposure. But one of the only techniques that limits the probability of having an arc flash at all. So this is working before you have an arc flash. Everything else is working after you get an arc flash to minimize the time that the fault is on the system. So both NFPA 70E and Z462 say that high resistance ground flash mitigation technique because it reduces the likelihood of exposure. And the red book, the green book, and the buff book, they all say the same thing. So let's look at the economics of a high resistance grounded system. So when you have a solidly grounded system, you're going to run the neutral to service 277 volt loads. And that's going to cost you material and labor. You have a neutral conductor, so you have to put LSIG for your feeder indication, specifically if more than 150 volts to ground and greater than 1,000 amps. So you're looking at the total cost difference between the solidly grounded system and a high resistance grounded system of $12,500. So it's less high resistance grounded system than a solidly grounded system. Now, one thing you are sacrificing is you don't have the use of the 277 volt load. But you could put in isolation transformers where you're servicing 277 volt loads and end up with a safer system. So just unground the system, the only advantage unground the system has is that you can have process continuity when there's a ground fault present. Solidly grounded system, you have control over the transient overvoltages and the ability to locate a ground fault. Obviously, you located the ground fault because the circuit breaker that was protecting that feeder tripped. And now you have to go look for a fault. But high resistance grounded system gives you process of continuity, control transient overvoltages. You can locate where the fault is without shutting anything down. We've actually put CTs around conduit, and we can actually locate the pulsing in the ground fault circuit. Prevents damage in short transformers or rating machinery, reduces the likelihood of having an arc flash. So this is the advantages you get with a high resistance system. But that was just a regular high resistance grounded system. We've also developed a smart high resistance grounded system where you have selective instantaneous feeder trip. Again, the threat of having an ungrounded system was if you had one fault on the system, you can't find it. But if you have a second fault on the system, then you have a phase-to-phase fault, phase-to-ground-to-phase fault. Something has to trip. It may be one feeder, maybe the other feeder. It could be the main breaker, but something has to trip. With a smart HRG system, we give you second fault protection, which basically means in a critical process, you can determine between two feeders which one has higher priority. And the one with the lower priority will trip, keeping your critical processes running at all times. We can mitigate 95 to 98% of all arc flash incidences because it's a high resistance grounded system. We can help you locate where the fault is. The A is assisted fault location. R, resistor monitoring. In Canada now, there's a code requirement that says you have to monitor the integrity of the resistor. We've always had it in mining, but now it's in the Canadian electrical code, so you have to do that throughout. And time selective feeder isolation. So if we had one particular customer who said, I don't want my electricians to become complacent, so I'm going to give them 8 hours to find the ground fault. If they don't find it in 8 hours, I'm going to trip right away. So you have time selective feeder isolation. You have 8 hours to find the fault. If you don't find the fault in 8 hours, if it still persists, we're going to trip that feeder. And I located ground faults in facilities that I've never been in before in less than an hour. Any size facility with this type of a system, I can find the ground fault in less than an hour. So trip delay after first ground fault. That's one of the benefits we got from the smart high resistance, smart HRG system. So you can program the feeder modules to trip on the first fault after a time delay. Process continuity of critical process with second fault. When you have one fault, you can still operate with one fault because the code says you don't have to isolate. If you look at 250.36, it says if you limit your fault current to a low value, and if you're less than 1 kV, you don't necessarily have to trip. Whereas Canada says in 10-1100, no, 10-300, used to be 10-1100. In 10-300, it says current to a low value, 10 amps or less on systems 5 kV and below, you don't have to trip. NFPA 70E and Z462 says if you have a high resistance grounded system, you have an arc flash mitigation technique, so you don't have to trip. The feeder with the lower priority will isolate and will isolate quickly before the instantaneous of your feeder breaker. Reduce the magnitude of the arc flash. Okay, now you're going to have to bear with me on this one. 70E says reducing the magnitude of severity or of exposure. An arc flash relay will typically detect the arc flash and trip quickly. So we had some customers that came to me and said, resistance grounded system, but I can't change the label. Why don't you develop something that allows me to put in the high resistance grounded system and be able to change the label? So we came up with an arc flash for that smart HRG system, which allow you to do just that. You guys have seen these before, right? In 1 second, 0.1 second cable fire, 0.15 seconds copper fire, and 0.2 seconds steel fire. No electrical industry. All we're trying to find out here is that incident energy is directly proportional to time. This is why you have to have zone selective interlocking, zone differential protection. We're trying to minimize the time that the fault is on the system and have faster reacting relays to trip when there's a fault in your system, because when there's a fault in your system, you're most likely will have an arc flash, but they only protect minor area of your zone differential protection. No, sorry. Differential protection only protects a piece of equipment. Arc flash relays only protect a piece of equipment. High resistance grounded system protects your entire system, all of the return current that's coming in. It limits the fault current. We've also developed an interlock, not with current, but with pressure. So in this particular module that designed, it looks at light and pressure. Now, pressure takes about 10 milliseconds to elevate. So we're looking at isolating the protective device 95 to 100 milliseconds, which is still faster. And this is the module here. So we've got light inputs on the bottom from fiber, light inputs on the top from point sensors, and pressure sensor inputs on the left, top left. So you can interlock your piece of equipment with light in order to have check, shall we say, that you do have an arc flash. So not only do you have a smart HRG system that's telling you that you have minimized the risk of having an arc flash, we've also put in this relay to say, now you can reduce the energy in an arc flash and you can reduce the label. And we could do that because we're the only company that has the high resistance grounded systems. We manufacture the resistors and we manufacture the relays. So if you want something special, you come to us and we can probably do it. The arc detection relay, so we have obviously we're looking at the differential pressure between the inside of the cell and the outside of the cell. So that's how it's going to work. Then we trip right away. We have an arc flash, sends a signal back, and we trip. Now with Smart HRG, we cover everything. So the total system approach, exclusive offering, only company that provides high resistance grounding and arc solutions. Increase safety, reduce the risk of electrical arc flash, increase reliability. Just in case we had another arc flash, I just wanted to make sure we had that. And it's an economical solution. Increase reliability. So I've also heard from many people that they try to increase redundancy, but increasing redundancy does not increase reliability. So we're increasing reliability without adding more capital, and it's a more economical solution. I'd like to turn it back to Mike, and thank you all for your patience with me this morning.
All right, thanks, Sergio. Great overview for everyone about the different options out there to address arc flash and what I-Gard has to offer to the market. A few of you in the audience have already submitted questions, so we're going to jump right in and start addressing those. If you would still like to submit a question, again, type your question into the question window on the side of your screen and just hit the submit button. And with that, I'll jump over to a few of the questions here, Sergio. So one of them is, for long cables, do you recommend 59N protection to avoid undetected high impedance ground faults?
Is this for a solid grounded system or for a resistance grounded system? If it's for a solid grounded system, I don't think long cable lengths are going to do much. It's not going to change the voltage on the neutral. So I'm not sure how exactly to, but I'll tell you what, send me that question. Maybe there's a little more to it and we'll take a look at it.
Yeah, there was no other info provided, so maybe the submitter can add a little bit and we can jump back to it if I see it pop back in.
Sure.
All right. Next question would be, can just about any solidly grounded system be replaced with a high resistance grounded system? And
Great
are there any
question.
examples where HRG is maybe not the best solution or not usable?
Okay, I wouldn't use H when you have a 122 volt system because most of your load is going to be 120 volts. So you have a distributed neutral, you're probably not going to benefit with the HRG system on 12208 because of the neutral being distributed. At 480 and 600 volt in Canada, most systems can benefit from the HRG system because a very, very little of your load is going to be 277. And now with the onset of LED lighting, probably practically nothing is going to be 277 volt. But going back, can any system be converted to an HRG system? No, not any system. And so some systems require a little bit of engineering because what has to change? Any that are phased to ground. If you have utility metering, they're typically going to be 360 to 120 volt PTs for the metering. They're not going to work. So you're going to have to change the PTs or have a different type of system for metering. There are some MOVs or TSSs that you need to make sure will work with the HRG system or be replaced. But the biggest thing that's problematic is slash-rated devices. So usually IEC components in your switchgear or in your facility may not necessarily be compatible with the resistance grounding system. Not that it's compatible with the resistance grounding system, but incompatible with the escalation in voltage that's going to result from a ground fault. I don't know if that answered your question, but
I think it did. So hopefully that person understands that a bit better. Another question was, what's the difference between just a neutral grounding resistor and a high resistance grounding arrangement?
Okay. When you have a neutral grounding resistor, you can divide that into two categories: high resistance grounding system and low resistance grounding system. So on medium voltage, you're typically going to have a low resistance grounding system. So on a 5 kV generator or 5, you're going to have a resistor that's on your source, and you can have a 6 ohm resistor. 6 ohms is a low resistance, but a high current. So you're going to develop 400 amps of fault current on a ground fault to appropriate feeder. A high resistance grounding system limits your fault current to a low value. So because of Mr. Ohm, a high resistance is a low current and a low resistance is a high current. But the voltage practically behaves the same.
Okay, great. Here's another question for you. I've read there's no industry standard for testing light-based arc detection because the installation isn't provided by the manufacturer. I guess they're saying of the equipment. Has that changed? And is there some kind of standard or listing for that type of arc flash protection?
You know what? I'm not 100% familiar with this. If I can, I'd like to answer this later because I need to do some research and see what standards are available. But I believe there are some standards like C37.20, which 20.7, which allow this. But I don't know what the testing requirements are.
Okay.
And that's for. But I'd like to answer that one later if I can, after doing some research.
No trouble. One good thing is the questions when they come in, we've got the person's contact information, and you can follow up directly with them to either get a better idea of exactly what they're looking for or to provide some time for you to do a little research like you just said. So that's fine. Let's see, by having an HRG system, does the arc flash hazard increase in energy as a result because of a delay in the response time with the OCPD versus a non-HRG system?
The HR, okay, increase in the incident energy or decrease in the incident energy, is that what they're asking?
Yeah, by having the HRG system, does the arc flash hazard increase in energy because of a delay in the response time?
Having the HRG system does not incident energy unless you put in the smart HRG system, in which case it will decrease the incident energy because you're going to trip faster. But just having the HRG system does not change incident energy at all.
Okay, great. I guess this is just kind of a basic question, but it's probably a good one. What do I have to consider for installation of an I-Gard system in existing equipment? So kind of going back and retrofitting an existing system.
Well, if it's already high resistance grounded or ungrounded, there's really nothing to consider. But if it's a solidly grounded system that you want to convert to a resistance grounded system, you look at your and make sure they can be made compatible. And the reason why we have to look at whether they can be made compatible is that often manufacturers make conversion kits, so you can remove a couple of screws to help make the system more compatible with the resistance grounded system. So if you read some manufacturers, they say, and sometimes it's difficult. So if you send me the manufacturer and the type of the variable frequency drive, I can help you look, because some manufacturers, they play with words, so you really don't know what you're looking for. So typically you have to remove the MOVs because of the escalated voltages, and on some of them, the common mode capacitors, some of them just especially IE VFDs, some of them can't be converted.
So Sergio, I guess that follows with this question here, because somebody else asked, what modifications need to occur for mechanical equipment, AHUs, fans, pumps, chillers. So that applies to those types of equipment as well, correct?
Yes, it does. And the only thing that needs to change there is the variable frequency drive. Nothing on the motor has to change, and nothing else has to change. Just the variable frequency drive, because some of them have MOVs on the front end, and we want to make sure that either if they're rated for the line-to-line voltage, we don't have to do anything. But if they're not rated for the line-to-line voltage, we have to remove them from the circuit.
Okay. How many test cycles can the AVT do if there is no power on the three-phase connections?
We've tested up to about 15 test cycles, but we've since modified that in that, because one customer says their procedure is to come back after some time to ensure that the system is de-energized, and sometime for them meant in excess of a week. So we've put in a port where you can charge the capacitor in about a minute so it's fully charged externally without having the power on, and you have another 15 cycles to do after that.
All right, thanks for that clarification. And this will probably be the last question before we run out of time. Wondering if I-Gard Sigma TDM can be powered from the relay itself instead of needing a separate external power. I guess they were doing some construction and commissioning and ran into a bit of trouble. So that's what generated this question.
Yes, and that's from, yes, it does and it can. We've modified that since, and now the Sigma 3, I believe, the TDM and the Sigma 3 off of the Sigma. So, and you connect it with an IX cable, and the new documentation for that will be out shortly. It's just making sure that we get all the testing done on it first, but it's ready to roll out fairly soon.
Okay,
yes,
great.
It was a problem with the external power supply, but we don't have that problem anymore with the new device.
Perfect. Okay, great. Well, we've gotten to a point where we've run out of time for today's session. And I'd like to once again thank Sergio for delivering a great presentation and sharing his knowledge and experience with everyone here today. And I'd like to thank I-Gard Corporation for sponsoring today's event. They made it possible for us to bring this to you, so We appreciate their support, and we enjoy partnering with them whenever we can. And with that, I hope everybody has a great rest of the day, and of course, be safe out there.